we are continue from yesterday. Okay, the one I think yesterday we stopped at the H parameters. Okay, so just a little bit recaps of from yesterday's class. Yeah, so okay. Wait, not this slide, but I want to show you the which slide? Yeah, this slide. Okay, so is AC equivalent circuit, yeah, AC equivalent circuit models to solve the AC circuits. Actually, there are a few models that you can use, yeah. So the first one, okay, the first one, which is this is a very traditional part. Okay, this is very old techniques. Okay, this is very old techniques. This techniques is usually is widely used before R model, parameter R model or RE model is introduced. So that's why at beginnings, people are using a hybrid H model to solve the AC equivalent circuit, and that's why if you are looking into yesterday's yeah. Well, I haven't put yet the yesterday's recordings inside the what, yeah. If you look at here, yeah, it's very complicated. No, it's not in it's quite what, you know, there has lots of a subscript to for okay, for H model. Okay, so it looks very like very complicated, and it's quite difficult for you to understand. All right, so because this is what techniques that use before the RE model is introduced. Okay, so RE model, where's the slide? Okay. So RE model, okay, is later has been introduced to solve the AC equivalent circuit. So okay, so RE model, okay, RE model, what's the difference? Later on, we're going to look at the difference between RE model and H parameters, okay? So RE model, the parameters, yeah, are defined, all the parameters inside the RE model or R model, okay, are defined by actual operating conditions, yeah? They are used by using the actual operating conditions compared to H models. H models, not H model, sorry, H parameters or hybrid model, they are using general terms for any operating conditions. That's why there are lots of subscript here which refer to specific part. For example, if I can show here, for example, HIE is referred to input impedance at the emitter. HRE is referred to the ratio at the emitter. So there are lots. They are using the general terms for the operating conditions. Yeah, despite for RE. Okay, they are using the actual operating conditions. All right, so since that some of you are asked about RE model, okay, RE model, basic of RE model, actually it's look like this, okay, where parallel to the collector, there are internal, we call this like an internal resistance, yeah, there are internal resistance at the collector, which is R prime C. Dia baru masuk kejap. Okay, R prime C, and then R, and also at the base there are R prime B resistor, and at the emitter there are R prime E resistor. Okay, but this resistor, okay, these two resistor can be neglected. Why? Because RB resistor is too small, This is too small, so it can be neglected and it can be assumed that there is no resistor at this part, okay, and it can be short circuit. It can be short circuit here. And RC parameter, RC resistor is too big, is too large. The value of the resistance is too large, and we can say that the currents will not flow here at all. Most of the all the currents are going to flow directly towards here, okay, instead of flow to here. So this is going to be an open circuit. So this parameter can be omit. It can be neglected, okay, and left behind only these parameters, okay, only these parameters. And the currents flow at the collector here, okay, at the collector here, okay, we can say that alpha AC, okay, alpha AC, AC represents to the AC currents, yeah, alpha AC IE is equals to IC, okay, alpha IE is equals to the currents at the collector. And also we have learned before that IC is also equals or approximately equals to beta IB, right? IC is equals to approximately beta IB. So since that these two can be, these two represents to currents at the collector, so it can be, we can say that it is approximately equals, right? And then so you can rewrite it like this, okay? And you can write it like this, and then from here it can be like this. All right, okay, so how the AC equivalent circuit we're going to look like? Okay, AC equivalent circuit we're going to look like this, right? Okay, for example, as I mentioned before, okay, as I mentioned before, I showed before that IC current is equals to beta IB, right? Okay, IC is equals to beta IB. So this is what, this is something is common that you have to remember, all right? So IC is equals to beta IB, and this is currents that flow at the emitter, okay? And this is a forward bias diode because the currents is flow from here and compared to here because this is ground, so this is 0 and this is lots of voltage here. So it is a forward bias. That's why it can be represented as a diode. And since that there is a resistor inside here, okay, resistor inside here. And since that there is a resistor inside here, so instead of draw the diode, you can replace the diode as a resistor RE because there is a resistor inside here. Okay, next. You need to know how to represent the transistor as an AC equivalent circuit. Okay, you need to know how to transform this circuit into this circuit. I think, I hope this there's no problem for this, yeah. But I'm gonna explain that a little bit. Okay, so this is imagine that this is a transistor. Yeah, actually, there is a transistor here. Okay, where this is the base, this is the collector, and this is the emitter. Okay. To redraw from this circuit to represent it like this, okay, what should you do is you should know where is the base, where is the emitter. Okay, if you look here, the base and the emitter is connected. This is the input part. So the input part, there is a base, okay, base, and then there is a RE here. Okay, this is the RE. And then this is the collector part. This is the emitter part, yeah. This is E part. This is the B part, base, yeah. RE. So as when you look here, okay, ZI is equals to beta RE. Why? Because this is the impedance, right? This is the impedance, and then wait. The currents that flow, why it can be like this, okay, why it will be IE, why IE is equals to beta RE is because if you look here, IE is the currents that flow from base and also from collector, right? current flow from collector and plus with the current flow from base. Okay, so current flow at the collector is equals to beta IB, right? Beta IB. So plus IB and then times with RE here, okay? So from here, okay, from here, you can factorize this part. So it will be beta, sorry, not beta here. Sorry. So it will be IB beta plus 1 RE. Okay, beta plus 1 RE. So since that this plus 1 is too small, so we can neglect or we can omit this part. So it will be VBE, it will be beta IB, beta IB RE. Okay, beta IB RE. Okay, so from here we can say that since that we want to find the impedance, right? So this is the Z, right? The impedance of ZI is here. Okay, so ZI impedance of here. So ZI impedance. Why it is impedance and not resistor? Because this is impedance means, as I mentioned yesterday, right? Impedance means the effective resistance of electric currents from here. So effective resistance at here, at this part. So since that we already know BBE is beta IBRE, so to find the impedance is, we can use Ohm's law, V equals to IR. Okay, V equals to IR. So to find the impedance is Z, right? So V over I. So V is, we are using VBE since here is VBE, yeah? So beta IB RE, because this is the value of VBE, over the resistor value here is RE. Over IB, sorry. Over IB, because IB is flow here. Sorry, yeah? Over IB. R is equal to Z over I, correct? So over IB, so IB can be cancelled out, so it will be beta RE. So that's why the value here, sorry, the value of impedance here, okay, it can also represent as beta RE. Okay, and you can write it like beta RE here. So beta RE here represents the impedance here. Okay. Okay, be careful that it is not same with resistor. Resistor is only resistor at the emitter, but impedance is the total effective resistance at this part. Okay, so that's why it can be represent of beta RE here. So it represents that the total effective resistance at this part. Okay, so clear at the input. So this is the input. Let's look at the output part, which is the collector and the emitter part. So here, okay, the collector, there is no resistor. There is no resistor at the collector. So at the collector, you can draw straight line, and there is a diamond here. What is the meaning of the diamond and currents here means? This is what we call transconductance. Yeah, transconductance. Okay, transconductance. It means that the currents flow here, the currents flow at the collector here is depending on the currents flow at the base. This is dependent current. Okay, the current is depending at the current at the base here, right? So that's why the flow, the symbol is like this. Okay, it shows that the currents here is depending on the current or at the base here. All right. And since that this collector is connected directly to emitter, okay, connected directly to emitter, so this can be combined together. Okay, this can be combined together, emitter and emitter, since it's same, so it can be it can be connected, and this can be ground. Okay, So the value here is actually IC, right? But IC is equals to beta IB. So it means that currents flow inside here is depending on the currents of IB value, right? So that's why it is look like this. Okay, so these are the initial, or these are the basic concept. These are the basic circuit view, or basic equivalent circuit. Sorry, basic equivalent circuit of AC AC circuit for RE transistor model. Okay, later on, in a real case circuit analysis, there will be combinations. There will be other combination where there's going to be a resistor here. There's going to be a resistor here, where we will look later on for others examples. All right. So far, okay. Go about this part.
Okay.
All right. So did you understand about the resistor now?
50-60% maybe
Okay.
people can better
Yeah,
understand.
yeah. Okay, so later on we're going to look into detail about how to solve uh, the real, I mean the real circuit analysis. Okay, so but for this, what we want to say is this is how the RE transistor model we're going to look like. Okay, this is only the basic of RE transistor model, how they're going to look like. All right, so this is only the basic part. All right, so for today, yeah.
Sensei, the impedance is due to the transistor one, right?
This impedance, the input impedance at the input.
The impedance is actually the transistor cause one, right?
Wait, impedance ZI or RE? Because RE is resistor, ZI is impedance.
The RE and GI is not the same.
Not the same. Okay, RE and ZI is not the same because ZI is impedance, RE is resistance at the emitter. Okay, RE is resistance at the emitter, which is this part. Okay, which is this part. But ZI is the impedance at the input here. Which is the effective resistance of this circuit at the input, which has a related to the VBE and also depending on the IB one. But RE is the resistor at the emitter. Okay, it is.
RE is from the transistor emitter part.
Yes. RE
Oh,
is the transistor at the emitter part.
okay.
Okay, all right. Okay. So when you want to draw the AC and AC equivalent circuit, we are actually take into account the impedance. Okay, we are actually take into account the impedance. All right. Is that okay? All right. Because this is already calculated inside here. This is already taken into account inside here. All right. So be careful from here. So that's why you have to understand the basic concept first. Yeah. When you want to draw the AC equivalent circuit, we're gonna take into account the impedance at this part. Okay, because the impedance is take into you are already calculated the with RE. You are already calculated with IB and VBE as well. Okay, so impedance is much more accurate compared to resistor here, because resistor at the RE, resistor at the RE here, it is not affected by the not affected. I mean, it is not effective resistance compared to impedance. Okay, so these are the concept or the step that you want to draw the AC equivalent circuit from the RE transistor, from the transistor. Okay, I think later on, if you look into the examples of the circuit analysis, it will be much more easier to understand. Okay, so let's proceed to the pi model first. Okay, transistor hybrid pi model. Okay, hybrid pi model. Okay, hybrid pi model. Okay, it, this is another steps. Okay, for another method. Okay, for you to solve the AC equivalent circuit. Okay, by using the hybrid pi model. Well, the hybrid pi model are shown in relation to the transistor model. Okay, so this is actually just just information for you. An important hybrid pi model, there is R pi. Okay, there is R pi. For R parameters, there is RE, right? If you still just now, there is RE. But for hybrid pi model, there is R pi instead of RE. It is replaced by R pi here. Okay, R pi. This is also R pi. Okay, and it appears as a small AC resistance between the base and emitter. So this is same as RE just now. Okay, if RE is here, okay, RE also represents or symbolize the small AC resistance between the base and emitter. So R pi also same. Yeah? It appears as a small AC resistance between base and emitter. And for this hybrid pi model, when to use? Okay, when you want to use these techniques to solve the AC analysis, when the high frequency transistor applications, yeah, in high frequency transistor application, and also lower frequency resistor. Okay, and it is for lower frequency, it is closely approximate with the RE parameters. Okay, for lower frequency case, the solution, okay, is approximately same like RE parameters, and it can be replaced by RE parameters. Okay, so let's look into hybrid pi model here. Okay, hybrid pi model. Okay, hybrid pi model. So there are R pi here. Okay, there are R pi here. Okay, so same as just now. Okay, same as just now. You need to draw the AC equivalent circuit for this transistor. So the circuit same, basically same as RE model, but there is an extra RO here. Okay, there is extra RO. So in some cases, okay, in some cases, RO can be neglected. Okay, so this is depending on cases of the circuit. Yeah, if the RO is very high, okay, if the resistor here is very high, okay, it can be neglected, and we can assume it as an open circuit. RO is actually, okay, RO is, where did RO come? RO is actually the resistor at the collector here, yeah, resistor here. So yeah, so since as I mentioned just now, for same as RE, when the resistor here is too big, yeah, still remember at the what RE model just now, there is a resistor R prime C here just now. Okay, for this hybrid pi model, it is represented as RO. So in some cases, this RO is very, very large. So same as RE pi model, sorry, not RE pi model, RE model just now, R parameters. This can assume as an open circuit, and we can assume that there is no here, it can be neglected. Yeah. All right, so another thing for hybrid pi model, okay, hybrid pi model that you have to pay attention is, despite from the can represent as R pi in these cases, there is also, okay, the transconductance here. Okay, the transconductance here can be represented as GM V pi. Okay, in these cases, yeah, for pi model, hybrid pi model, if for R parameters just now, this is only represent as beta IB, right? Beta IB. But in this pi model, okay, beta IB also can be represented by GM V pi. So what's are the difference between these two? Okay, for beta IB, okay, beta IB, it is also known as CCCS model, which is current control current source. What does that mean? It means that the currents here, currents at the collector here is controlled by the current at the base here. So that's why it is known as beta IB, which is currents that flow at the collector is controlled by the current that flow at the base here. So it is also known as CCCS, okay, current control current source, and it will represent as beta IB, okay. And in some cases, okay, in some cases, the it can also, okay, the IC here, IC value here can also be represented as GMV pi. So what does that mean? It means that voltage, okay, the currents here is controlled by the voltage at the base here, V pi here, okay. Voltage control current source. It means that the voltage of V pi here, okay, V pi is actually IB times with the R pi here, okay. So V pi here controlling the currents that flow at the collector here, okay. So VCCS, okay, model, which is GM V pi. Both of these same will represent IC, okay, currents at the IC. Okay, both of these represent IC. So you can use either beta IB or GMV pi. Either one is okay. All right, either one is okay. So it depends on what information has been given to you. Okay, if the information that given to you the value of V pi here, so you can use the GMV pi to find the value of IC here. So it means that you are using VCCS model. But if the value of IB is given to you, you can use the CCCS, which is the current control current source model, where you are using the beta IB here. All right, so these are the informations, which model that you want to use is based on what of information is given to you. Okay, so as I mentioned just now, the RO here can be neglected if the value is very high, okay, because we can assume that it is an open circuit here, yeah. So equivalent voltage temperature VT equals to 26 millivolts at room temperature, which is 25 degrees. This one, let's look at the next slide, yeah. So this is the next slide. Okay, so as I mentioned just now, yeah, transconductance GM here, all right. So how does it can be represented as like this? Okay, this is RE model just now, yeah. Okay, this is RE model for your reference just now. Okay, this is the transistor that we will use the hybrid pi model analysis. All right. So these are the resistor. Okay, this is the base part, and then this is the emitter part. Yeah, this is at the emitter part, and it's given to you V pi. Okay, it's given to you V pi, which is V pi is also the value of BE here. Okay, if there is no resistor, if there is no resistors, any resistor, so it means that the value of VBE here is equals to V pi. This is actually V pi, eh? V pi. Okay, so V pi, and there is also R pi, of course. It's inside the emitter. There is resistor, right? So R pi, and then at this, since that this is given to you V pi, so you are using voltage control current source, VCCS. So the symbol that represents at the IC here should be GM V pi, because we are using VCCS. Okay, and then this circuit represents that there are RO here. Okay, RO value here, which is resistor at the collector here. Okay, all right, and it is the equivalent circuit is look like this. All right, so next let's look how we want to solve the R pi, how you want to find the R pi here. So R pi can be found or can be solved by using of R pi here can be solved by using beta over GM. Okay, how did we get like this? Okay, first of all, let's look at the transconductance. Yeah, so transconductance GM. Okay, GM is the transconductance. Yeah, transconductance. transconductance. And the formula or how to solve the GM or this transconductance, it is actually I at the output divide with the V of the input. Okay, when this can be used when V output, the rules is when V output is equals to 0. Okay, when V output is equals to 0, or we assume that V output equals to 0, then only you can use this formula. So inside this case, in this case of this hybrid pi model, the input is the output current is IC, right? So IC over V input. So V input is VBE. Okay, VBE here. So in this case, it's equals to V pi here, yeah? So IC equals to, so in this case, VBE is equals to V pi. V pi, and this when VCE, when the value of at the VCE here, CE, is equals to 0. Sorry, is equals to 0. Okay, so and there is, yeah, and IC can be over, okay, IC can over with VT at room temperature. In some at room temperature, yeah, at room temperature, okay, at room temperature, IC is over, okay, IC can be divided with the VT. What is VT? VT is the voltage equivalent of temperature. Okay, this is only happen when room temperature, and the value of VT is usually constant, which is 26 millivolts. Okay, 26 millivolts. Okay, you can see here 26 millivolts. These are the constant value for VT at room temperature. Okay, so in this case, IC, sorry, it's not enough here, so I'm going to use here. Yeah, in this case, IC will can be divided with 26 millivolts. 26 millivolts. So these are the value of GM. Oh, sorry, this is should be because I'm using a small IC. Oh, sorry. Okay, yes, this is capital IC. Okay, if you I want to focus here. Yeah? If you realize here, yeah, pen color. Let's use different pen color. If you realize here, I'm using here is IC, a small IC, and I'm using here capital IC, sorry. I'm using here capital IC, and at last also I'm using capital IC. What's are the difference? The difference is IC here is represent for AC currents when the source is AC source. Okay, so we also say that sorry, not also say IC here is sorry, wait, yeah, okay, IC here is represent when the source of the voltage is AC source. IC capital here is represents when the current is at DC source. Okay, and when the current at DC source. So in this case, we can say that since that VC is equals to 0, we can say that this AC source it can be equivalent to DC source. Okay, in this case, yeah, in this case, we can say that it can be equivalent to DC source. So that's why I'm changing from I small letter to I capital letter. Okay, this is just for your information. I want to show how to get this one. Yeah, okay, because in some cases, in this case, yeah, this AC current is equivalent to DC current. DC current. So that's why I can change from IC small letter to IC capital letter here. Okay, and then this IC can be divided with the VT, which is voltage equivalent of temperature. And since that the value is 26, that's why the GM is equals to GM, which is transconductance here, is equals to IC over 26. Okay, I think up until here, I hope it's okay, right? So if you are questioning why in the beginning I'm using IC and at later I'm using capital IC here, is because it is changing from AC source current to DC source current. Okay, because it is almost equivalent when VCE is equals to 0. Okay, so this is how we get. Okay, next. Now, in these cases, in these cases also can be used for RE model. Okay, for RE model here. Okay, I'm comparing these two circuits here. For RE model, okay, the value of RE is for RE model for this one, for RE is equals to 26, okay, over 26 millivolts, which is the value of voltage, okay, value of voltage. We are using Ohm's law, V divided by I, and I is I output, right? I output is IC, okay, IC. So it is will be 26 millivolts over IC. All right, so if you look here, RE model, it is the other way around compared these two. Okay, it is the other way around. And if we can also, that's why we can also rewrite that GM is equals to 1 over RE. Okay, GM is equals to 1 over RE, right? And 1 over RE. Okay, so these are the relation between these two, right? Okay, and then and how from here, okay, R pi, from here R pi. Okay, so R pi in these cases, okay, R pi is equals to beta over GM. Why? This is called from GM, R pi is equals to beta. Okay, GM R pi is equals to beta. No, sorry. R pi equals to beta RE. Beta RE. Beta RE. R pi here. Oh, okay. Sorry. Okay, wait. How from here R pi is equals to beta over GM is because they are comparing these two. If you look at this part, if you look at this model, both of this model, we are looking at this two model. Yeah, this is hybrid pi model and this is RE model. This R pi can be equivalent to beta RE. Okay, beta RE. So that's why R pi. Okay, because we are comparing these two, is equivalent to beta RE, and it can be rewrite as, since that beta RE, okay, RE is equals to 1 over GM. Okay, from here, right? From here, RE is equals to 1 over GM, and that's why R pi it is beta over GM. Okay, that's why R pi is beta over GM, because this R pi and this beta RE is what we are comparing together. Okay, and it can be rewrite as R pi equals to beta RE. And from here, okay, from the transconductance value, which is from transconductance of RE and GM, we can rewrite and we can write as GM equals to 1 over RE, and rewrite again this equation, RE is equals to 1 over GM. So once you get this RE value, you can include, or you can substitute into this equation. So you will get at last R pi here is beta over GM. Okay, I think how this formula get it's not quite important for you to know, but it's good to know where's the origin. But if you think that it is quite difficult for you to understand, you can just memorize this. You can just memorize this value. All right, you can just memorize this value, right? And for the RO, okay, RO, sekejap tadi ada orang masuk. And for the RO part is equals to VA. Okay, what is VA? VA is the early voltage. Okay, early voltage, and usually the value is between 150 to 250 volts. Okay, this is the early voltage. Okay, usually it is given inside the circuit informations. The value is between 150 to 250 volts. Yeah. Okay, so in this case, they are using 200 volts. Yeah, 200 volts divided by RC. Okay, RO here. Okay, to find the value of RO. Okay, in this case, RO is not large. It can be calculated. Okay. Okay, so these are where the information, these are where the formulas about hybrid pi model. Okay, so let's look at the, this is at the summary of hybrid pi model. I think up until here, maybe some of you thinking it's quite confusing or it's quite complicated, right? Yeah, Koshi like that, right? But we're gonna look into details about the circuit analysis later on, yeah? All right, so this is the hybrid pi model summary. Okay, so this is the VCCS model. Okay, so as I mentioned just now, VCCS is what? VCCS is voltage current voltage control current source. It means that the voltage V pi here is related to the that control the currents of IC that flow inside here. Okay, so this is CCCS. So remember the first alphabet C, so it means that the currents. So currents at the base here is controlling the currents that flow inside the collector here. So in this case, we are using beta IB. Okay, so VCCS, you are using GM V pi. All right. So the equation that you need to remember for all these things, yeah, for all the parameters. Okay, so beta equals to HFE, which is this is used for relation between the H parameters and R parameters. And then this is RO just now. Okay, how to find the RO? So RO equals to, this is in H parameters. For H parameters, RO is equals to 1 over HOE. Okay, output emitter. Okay, output at the emitter. For the hybrid pi model, hybrid pi model, it is VA, which is what is VA? Early voltage. Okay, early voltage, usually the value is 150 to 250 volts. Okay, and then divide with the value of IC. Okay, IC here is direct currents. Yeah, and then GM, transconductance. How to find transconductance is equals to IC over VT. Okay, VT is the temperature, voltage at room temperature. Usually the value is 26 milliamps. Okay, the value is constant. Okay, and you can find the value of IC or GM, right, from this equation. And R pi is equals to beta over GM. Okay, beta over GM. So these are the equations, important equations that you need to remember. Okay, which is summarized from all this, all the three parameters just now, which is from R model, H model, and also hybrid pi model. Okay. Okay, now after this, let's look into exercise for this part. Okay, this is the common emitter. As I mentioned yesterday, we will focus about common emitter circuit. Okay, we will not focus into common collector and common base. Okay, common collector and common base only for you need to know only how to identify or how to differentiate between common emitter, common base, and common collector. But for circuit analysis, the one that you need to be focused on is common emitter. Okay, so in this case, is common emitter fixed bias. Okay, the bias is fixed without bypass. Okay, this is without bypass capacitor. So it means that there is no capacitor at here. At the bypass capacitor, yeah, bypass capacitor is located at the emitter part of the transistor. So this is without bypass capacitor. Okay, this capacitor is coupling capacitor. Okay, so you also should know what is bypass capacitor, what is coupling capacitor. So in this case, C1 and C2 is coupling capacitor. Bypass capacitor usually located, not usually, always located at emitter. Right. So in this case, that it is without bypass capacitor. So there is no bypass capacitor at the emitter here. All right. So let's look. So these are the real circuit. Okay, these are the real circuit. So first, to solve this circuit, you need to simplify this circuit as simplify the circuit as AC. Sorry. Allah. As AC equivalent circuit, right? Okay. So assume that you already know all the informations of IB and IC and all those things, yeah? But if we haven't know the value of IB, IC or VCE, then you have to find it first using DC equivalent circuit, yeah, DC analysis, right? Okay, so this one, yeah? So to solve this, first set all the DC source to 0 ground. So identify first, where is the DC source? So these are the DC source. These are the AC source. Okay, so this source should be grounded. Okay, should be grounded, or we assume that it's going to be 0. So set all the DC source to 0 or ground. Next, replace the coupling capacitor and bypass capacitor with short circuit. So it means that you just connected these two circuits together. Okay, with short circuit, and then rearrange the circuit to make it simple and draw the AC equivalent circuit. Okay, now the RB here, RB and RC here, since that this is can be short, this also can be short, we will redraw this circuit to as a simple, where RB here is also parallel, okay, is also parallel to RS here. So we draw the RB here at here, okay, which is also will be parallel to RS. In this case, yeah, parallel to RS and also parallel to RC. All right. Okay. Okay. Next, from the circuit here, let's draw a hybrid pi model. So in this case, we're going to use hybrid pi model. It's easier. Usually, we are using hybrid pi model because hybrid pi model is much more, is combined of those R model and H model. Okay, so you are using hybrid pi model here. So if you look at this part, yeah, VS, RS, and RB. So VS, RS, and then RB, and then this is going to be the input part, right? This is input to the base and the emitter. So this is the input of base, and this is emitter part, right? This is base and then emitter. So current at the base start after, okay, current of the base, we can also pay attention at the current of the base here. Current of the base here is counted after it go through these two resistor. Okay, it's not start from here, it start from here. Okay, so current of the base is from here. So this is current at the source here, yeah. And then V pi R pi, okay, they are using V pi R pi. And then since that they are using V pi R pi, so it means that this is VCCS, yeah. So they are using GM V pi. So V pi R pi, so it means that G pi V pi, GM V pi. And then the RC here is parallelly connected with the RL here. So RC, RL, and this is the V output. Okay, these are the V output. This is the input, V input, yeah, V input. V input is at this part. Okay, V input. Okay, this is the V input and this is the V output. Okay, so first of all, what you need to find from this, okay? So first of all, after you redraw the circuit, okay, we need to find the input impedance. Okay, what are the input impedance? Input impedance at this part. So input impedance is after take into account these two parallel. Okay, RB parallel with R pi. Okay, RB parallel with R pi. Okay, and then output impedance is RC. Output is at this part, right? RC is equals to RC. Z output is equals to RC. Okay, so let's look how. Okay, so let's look at the how to calculate the voltage gain. How to calculate the voltage gain? Okay, voltage gain is AV. Okay, so AVS. AVS here is represents as voltage source. Yeah, voltage gain at the voltage source. Yeah. Okay, so AVS is equals to voltage output, voltage at the output, okay, divide with the voltage of the source here. Okay, voltage of the source here. Next, voltage output, you can how to find the voltage of the output is by minus GMV pi, okay, minus GMV pi times with the RC and RL parallel. Okay, it means that you have to calculate these two total resistance first, yeah, and it is parallelly connected. And V pi here, okay, V pi here is equals to V input. Okay, V input, sorry, not V pi here, V pi here, yeah. V pi here is equals into V input, which is equals to, okay, V input is impedance ZI, the one that you have calculated just now, ZI over VS, VS, okay, VI is actually IR, right? So IR. R is actually the resistor, total input resistance, okay, input resistance just now that we have calculated just now, the input resistance just now, which is RB and R pi, okay, value of R pi here and RB parallelly connected here, okay, so this is the input impedance. So RB, after we calculated this, you will get the value of input impedance, just now. Dah hilang. Sekejap ya. VI input is equals to IR, right? IR. So R is input impedance with input impedance. First we look into R. Input impedance ZI parallelly connected into RS. Okay, ZI here parallelly connected into RS. Okay, so I here is IS. Okay, IS, and then IS is equals to VS over RS. Okay, VS over RS, so ZI RS, and then get the value. Okay, try, you will get this value, okay, ZI VS over ZI plus RS, okay, because this is I'm not calculating this value, right? So after you get the value, you will get the formula of V pi is going to be V input, which is also V pi. Okay, V pi here, you will get this value. All right. So, and then from here, you will get the gain. Okay, so gain means that VO over VS. So this value divide with this value. Where's the VS just now? So rearrange this one. Okay. Yeah, for if you get this value, yeah, V pi, which is this value. So rearrange, make the VS as the subject. Okay, make the VS of the as the subject. Then you will get A. Okay, A is equals to this value. Yeah. All right, and at last it will be like this. AVS is equals to GM over RCRL. RCRL parallelly connected. Okay, so this is parallelly connected. Okay, don't straight away put the value here. Yeah, it is not like that. Yeah, this is parallelly connected, so it means that 1 over RC plus 1 over RL. Okay, inverse. Okay, and then from here you will get from the Zi that you find just now, and then over Zi plus Rs. Okay, so these are the voltage gain for this model. And then from this you can also calculate the current gain. So current gain is output over input. Okay, always remember, yeah, the gain formula is equals to output over input. So it depends. If you want to find power gain, so power at the output over power input. If you want to find the current gain, current at the output over current at the current input. And then if you want to find the voltage, voltage at the output over voltage of the input. All right. Okay. Next, for the current gain, okay, I output, first you need to find the I at the output. So I at the output here is parallelly RC and RL. Okay, so this is RC and RL parallel times with the GM B pi minus. Why it is minus? Because there is a phase inversion. Okay, there is a phase inversion. Okay, that I mentioned before. Okay, inside at the input at the VBE. Okay, VB waveform. There is a 180 phase inversion at the VCE. That's why there is a minus here. Okay, there is a minus here. So minus GMV pi. Then there is the value of output, and then for the input is VI. Okay, VI equals to IZ over ZI. Sorry, I at the input. Okay. I at the input. I think in this case is here. Yeah. I at the input. Okay. Times with the input ZI input impedance. Yeah. And then from here, rearrange it again, make I as the subjects, and then you will get the value of the current gain is this. Okay, so try after this, try to solve. Either you will get a not of this current gain or this voltage gain. Okay, if you want to know how the formula how the formula is solved. Yeah. Okay, if not, you can always remember. If you want to remember, also okay. If you want to remember this step, also okay, right? But it's very good, or it's better for you to find the how to solve this formula. Okay, so that it's easier for you to understand, or easier for you to remember. Okay, so so it shows, yeah, in this case, yeah, since that we are, as I mentioned just now, so there is a phase shift in this hybrid pi model, yeah, because you can see here we are using minus GM. Okay, so it means that there is a phase shift occur inside this hybrid pi model. That's why we are using minus GM. And why it is minus, there is a phase shift occur, because I showed to you earlier, if you still remember yesterday at the beginning of the slide, which is this slide, yeah. So you can see here, yeah, at the BQ, okay, this is the input phase, input waveform, and this is the output waveform. Okay, there is always a phase inversion, okay, between the input and at the output, right? Okay. Right. Back to the slide. Where's the slides now? So in that case, this one, right? Okay. So this is how wants to solve the fixed bias without bypass capacitor. Okay, in this case. So let's look at the example one. So these are fixed bias without bypass capacitor. Okay, so first of all, draw the equivalent circuit and find the AV and AI. Okay, what they ask is, they said that you have to find the value of AV, which is the voltage gain, and the value of AI, current gain, which given to you that VCC is equals to 8 volts, VBE, okay, VBE is 0.7 volts, beta DC and beta AC same. Okay, so it means that in the DC case and AC case, both of it, the value is 100. Okay, so beta IB, so the value of beta here is 100. Okay, and the VT is 26 millivolts. So these are the currents of these are the real circuit. Okay, these are the original circuit. So first of all, what we need to do is we need to draw the DC equivalent circuit. Okay, this DC equivalent circuit to AC equivalent circuit. So since that is mentioned, there is a VCC 8 volts here. So it means that here, okay, so it means that at here, at this part, it is 8 volts. Okay, this is the VCC part, yeah, the VCC part. Okay, so first of all, make this into ground. Okay, we have to make it into, at this part, yeah, make it as ground. Okay, or assume it is 0. And then VI, all right, so, sorry, this is VI actually, VI, okay, VI, and then II is here. Okay, I is here, and then this capacitor, make it as short capacitor, and then there is RB, which is parallelly connected to here. Okay, RB parallelly connected, and in this case we are using V pi R pi. Okay, V pi R pi, and then since that, so this is the VCCS GM V pi, and then there is RC and RL here, yeah, RC and RL, RC and RL. So here is the input impedance, here is the input impedance at the RB here, and here is the output impedance. So output impedance is at here before RL. So it's mentioned already to you, the impedance of input is at here, and the impedance of the output is before RL. So be careful where is the location of input impedance and output impedance. Yeah. So output is impedance is here. So from here, once you draw the equivalent circuit here, next what you need to do is, then only we need to we can find the the value of AV and AI. Okay, so AV and AI can be solved using this formula. Okay, So in this case, I think in this example, okay, in this example, it will be very simple because there is no resistor at this point compared to here. Okay, compared to here. So you can omit this resistor part, all right? And otherwise it's same. Okay, so first of all, you need to find the impedance, input impedance. So input impedance is, in this case, input impedance Zi is equals to RB parallelly connected with R pi. So it means that 1 over RB plus 1 over R pi, okay, 1 over R pi inverse, okay. So the value of R pi just now, still remember, the value of R pi is beta over GM, right? Beta over GM, and value of this GM is 1 over IC over VT. Okay, IC over VT. Okay, so first, first by we have I skip this part. Okay, so when you do, okay, you draw the DC equivalent circuit first and find the value of IC first, and then with the value of IC, what the value of IC over VT, which is VT is 26 millivolts. Okay, so find the value of IC first, then you will get the value of IC, and then divide with the 26 millivolts. Okay, so with this value, okay, you can divide with beta, we're gonna divide with this value, then you will get the value of R pi. So once you get the value of R pi, put inside this formula, and then you will get the value of input impedance. Yeah, input impedance. And then after you find the input impedance, okay, after find the input impedance, so next you can find the voltage of gain. So voltage gain is the input, okay, the output voltage divide with the input voltage. So the input voltage here, okay, how to find the input voltage? V in here is equals to Vs. Okay, V in is equals to Vs. And then how to find V in? V in, the value is not given. Yeah, okay. So how to find V in is equals to the IB here. All right, IB is from here, right? This is IB. So IB can be calculated using DC equivalent circuit. And this part, RB here, the current step flow to here can be found. What are other information is given? VT, VC, VBE. Okay, so VBE is given actually, yeah. B, so B start from here, yeah. This is the B point. Okay, this is the B point, and this is the E point. Okay, so VBE is given, since that the VBE is given 0.7, so since that this is parallelly connected, so this is also, you can find the value of currents here. Okay, since that we know that VBE is 0.7, so we can find the I currents that flow here. So once you get these two currents, we can find the value of currents of II. So once you get this value of II, okay, once you get value of II, then we can find the value of V in. right? Mata. This is VBE kan. VBE is here. BE 0.7. So we know that this is 0.7. This happened actually here, yeah. VBE 0.7, and we can find the value of IB here. So since that this is 360 kilo ohm here, and then we can find II here, right? By knowing, we know the value of VBE here is 0.7, and here is 360. So we can find the currents that flow inside here. V in gonna be the totals of resistor. Okay. So to find II is equals to II here, right? Is equals to, this is two resistor, two parallelly connected resistors. So we know that R pi just now, right? So V in is equals to I in, sorry, II times R total resistor RB and R pi, right? Which is parallelly connected. So this value we can find. So II, V in and Vs. It is not given here, the value of V in. VCC 8, wait, yeah. From here, we can use Thevenin. Not Thevenin. We can find II here using, II here using, this one we already know. We can find the value of I here. So since that we know that it is 0.7 volts. Oh, okay. Since that we know that the value of VBE here is 0.7, right? So here is also should be 0.7. So V in also should be equals to 0.7. Sorry, because it is parallel. So V in also 0.7. Okay, so 0.7. Okay, if you know the value of V in, sorry. So once you know the value of V in, we can find so to get the V gain, kan, V AV, which is V output over V in. Okay, so we get, since that we know the value of V in is 0.7, so we can get also the value of V out. Okay, so V out is RC RL. Okay, RC RL, since it is here, right? RC and RL parallelly connected. So RC RL parallelly connected, and then times with GM V pi. Okay, so value of V pi can be found. Okay, and then value of GM just now. Okay, based on the equation just now, 1 over, IC over 26 milliamperes. Okay, so for this, first of all, you need to draw the DC equivalent circuit and get the value of IB. Okay, get the value of IC. Okay, and get the value of VCE. Okay, I think the most important value of currents is IB. Okay, once you know IB, you can always find these two value. Okay, because in this information, we don't know what is IB here. Yeah, so since that we don't know what is IB, we also can't find the value of IC, so we can't solve the value of GM. So first of all, draw the DC equivalent circuit to get this information: IB, IC, and VCE. Okay, and those all informations given, and then only proceed with the AC equivalent circuit to find the gain current, and also gain voltage and gain current. Okay, so the steps of this analysis, yeah, is quite lengthy, and usually it carries a lots of marks. Okay, so don't skip any steps, because if you skip any steps, yeah, you might lose some of the marks, and if you skip any step, maybe you get wrong somewhere of the value, and it will affect all of the calculations of the circuits. Okay, so once you get the value of IB is wrong, okay, all of the value are gonna be wrong. So be careful. All right. So the questions like this, yeah, usually will come out like one questions inside your test, inside your final exam. All right. Okay, so this is for common emitter, right? For voltage divider bias. Okay, so this is a voltage divider bias where you can see the resistors is extra resistors inside the voltage divider bias, right? So first of all, as before, same, you have to short circuit. Okay, short circuit the capacitor. Okay, so this is there is a bypass capacitor here, so you also need to short circuit this, and then and then you if you want to solve this kind of questions, yeah, you need to find the value, the Thevenin theorem first. Okay, the Thevenin theorem, use the Thevenin theorem to get the value of IB, and to get all the others information as well, the value of IC and IE. Then only you can proceed to the AC. This is the AC circuit we're gonna look like. Yeah, so the AC circuit, R1 and R2 will be parallelly connected, and this R1 and R2 can be represented as RTH based on the Thevenin theorem that you have calculated just that you have calculated at the DC source before. Okay, so our Thevenin theorem also is equals to R1 and R2 parallel connection. And then RS, this is the transistor model. And this is the IC, and this is IR. Okay, so voltage divider bias will not come out inside your inside your exam. Okay, so this is just extra information for you. Okay, so the exercise. Okay, these are the exercise example. So draw the AC equivalent circuit for the following voltage divider bias. Okay, so the question only asks you to draw the AC equivalent circuit. So the circuit we're gonna look like. First of all, this is the I. Yeah, this is the sorry, bukan macam ni. Jangan start macam tu. Okay, this is the AI, and then this will gonna be the parallel connection of R1, R2, and then okay, R1 and R2, and then this is the RE. So this is short circuit, kan? This is short circuit. So this is going to be RE here, yeah? Which is RE here. Okay, and then from here, there will be another part which is, so this is beta IB. So this will going to be RC, and then this is going to be RL, and then this will going to be V out. All right, so it's going to look like this. Right, so this is VI. Okay, so this is the ZI. Okay, so ZI is located before R2 and R1. So ZI is here, and then ZO is before RL. So this is ZO. Okay, so look, where is the position of impedance and position of input impedance and output impedance. Yeah, sometimes position of input impedance is located here, so it means that the impedance should be here. Okay, in these cases, the input impedance is located before R1 and R2, so it is located before R1 and R2, so it should be placed here. All right. So, and output impedance usually is always here, yeah, before RL, before the load resistance. Okay, but please check again, all right, before you decide where is the position of input impedance and output impedance. Yeah. All right. So next, these are the example. Another example: determine the values of ZI, input and output impedance. Gain for voltage and currents for the amplifier circuit below, and given VA, okay, it's given to you, yeah, VA is 200 volts, and IC, okay, so IC also is given to you, 2.37 volts. Okay, so first of all, draw this circuit as an equivalent circuit. So this is a voltage divider by circuit cases, okay, right? So first of all, from this circuit, draw to the AC equivalent circuit. Okay, so this is a VS, okay, and this is RS here, RS here, and then R1 and R2, okay, R1 and R2, and then V pi, okay, R pi, and then in this case there's GM V pi, so GM V pi is here, and then RO, okay, RO is equals to RC here, yeah, RO, and then, oh sorry, RO is RO. RO, and then RC, RC here, and then ada RL here, okay, RL. So the input impedance, so R1, R2, and R pi is parallelly connected. So it is 8.2 parallelly connected. So this is the value, yeah. And then output, so this is 1 over R1, 1 over R2, 1 over R pi, inverse, okay. And then the output impedance, yeah, RO and RC. So RO, just now RO is equals to 1 over, if you still remember, in the case of hybrid, this RO is VA over IC. That's why it's given to you just now the value of VA and IC. So RO is VA over IC. So calculated this value, you will get this value, and then you just have to parallelly connect it, and you will get this value. Okay. So once you get the value of this, you can proceed with this voltage gain, and then you will get current gain. Okay. So maybe after this you can try and give it a try, and you're gonna look how the exam. You can check the answer with your this answer. Yeah. Next, let's look this common emitter unbypass RE. Unbypass RE, what's that mean? It means that without bypass, yeah, without bypass RE. Okay, so the first of all, what you need to do is the removal of the bypass capacitor results in increase of the input impedance. Okay, once you remove the capacitor here, yeah, without bypass, yeah, once you remove the capacitor here, okay, what will happen? It will increase the input impedance at the ZI. Okay, it will affect the impedance at the input, impedance at the input, and also output impedance at the ZO, and it will reduce a reduction in voltage gain. Okay, voltage gain will reduce a little bit. Okay, so this is the unbypassed RE. Okay, so it means that RE is considered, yeah. So in this case, okay, input impedance, okay, ZI is wait, yeah. So from this connection, okay, from this connection, okay, change into AC equivalent. So it will be RB, okay, RB and RC. RB is between base and also emitter. So RB is located at here. And then RC is located from collector to emitter. So RC, collector to emitter. And from these two, okay, this bypass, this bypass I B pi R pi is inside here, and then GM pi is also inside here. So this is the transistors, yeah, inside the transistors, and there is an RE here. So it should be RE here, okay, and it will, yeah, this is how the look of the AC equivalent circuit, yeah, is quite different between others just now. Okay, others just now we assume that there is no RE here. So we can make this directly goes to down here. But now in this case, we are considering RE in this case. So at RE, there is another resistance. Yeah? You have to add, or you have to take into account. So in fact, inside this, the formula is same. Okay, the formula is same. First of all, find the input impedance. Yeah, so input impedance is located at before RB here. Yeah, so RB, okay, parallelly connected with ZB. Okay, now you have to find the ZB impedance, which is the ZB impedance is taking into account this R pi and also RE. So R pi plus beta plus 1 RE, okay? Beta plus 1 RE. Or you can also just beta RE because this is very, very small, yeah? Beta RE, so you will get the ZB impedance, yeah? So this impedance, this ZB impedance is just like imaginary resistor here. So it is parallelly connected with this RB. So that's why it is parallel. Okay, it is like imaginary resistor, which is ZB here. Yeah. So then you will get the value of impedance input. Okay, so the output impedance is same. Yeah, output impedance is always the impedance of RC because it is parallel. Yeah. And then from here, voltage gain. Okay, voltage gain same. Okay, there is a phase inversion. Okay, there is a phase inversion, so that's why it is minus. And then output divided by input. Okay, rearrange the conditions. Then you will get that the value of voltage gain is this. Yeah, this. So there is a condition where if GM-RE is more than 1, this GM times with this RE. Okay, so if this GM is more times with RE, it is more than 1. Okay, so it will be the output impedance. Yeah, you don't have to calculate the impedance of sorry, not impedance, the voltage gain is always RC. Directly take the value of RC, divide with the value of RE. Okay, why it is minus? Because there is a phase inversion, okay, at the output part. Okay, don't forget the minus part. Yeah, right. So this is only condition fulfilled when the value of GM is large times RE larger than 1. Okay, if it is 1, the value of GMRE 1, it will not fulfill this condition. You have to use these conditions, okay? So for current gain, this is output over input, okay? So you will get like this, okay? So this is current gain from voltage gain as well, okay? Later on, I forgot to include inside this the example of previous test questions related to this common emitter. So later on, I will put inside this inside your inside your e-learning, so that you can refer as well the previous test, okay, previous example test, collection of previous tests, okay. Okay, so next, common emitter unbypass RE to determine ZO using imaginary voltage source. So this is just extra knowledge for you that you don't have to know, okay, for this alternative approach. Because the one that will come out inside your exam is common emitter that you need to focus, common emitter with bypass. Okay, this is what you have to focus on, common emitter with bypass, and also inside your test also, it will be focused on hybrid pi. Okay, hybrid pi, which is GM V pi. Okay, GM V pi. But if you want to use beta IB, is also okay. Okay, because these two will give same information. Okay, the only difference is only current. This is current control, and this is voltage control. So you can decide which you want to use. Yeah, either this one or this one. Okay, but in your exam it will be focused on hybrid pi and also this, common emitter with bypass, okay. So later on inside your test, later on inside your e-learning, I will make example from previous test and also the solution, so that you can look into detail on how to solve from the previous past questions. Yeah. So this the example for unbypass RE. Okay, so unbypass RE. So this parts also will not come out, but if you want to try, you can give it a try. Okay. So again, I repeat, inside your test, okay, inside your test, what you need to know is, of course, you need to know this part. You need to know this part. Okay, you need to know how to differentiate between common emitter, how to differentiate with common collector, and how to differentiate common base. Yeah. So the example question might be like this. Okay. It might be like this. Okay. These are which you have to identify which is common collector configuration, which is the common emitter configuration, and which is common base configuration. So this is compulsory. Yeah? You need to know how to differentiate this circuit, and then you also need to know. Okay, this is for part one. Okay, so you also need to know the coupling of the capacitors here, the function of coupling capacitors. Sorry, the function of coupling capacitors and also the bypass capacitor. Please identify this function for each capacitors, please. Yeah, because if you lost mark at this part, I think it is very it is very rugi. Okay, sangat sayang, because this is very straightforward questions that you just need to memorize. You don't have to do any calculation for this. And then please focus on for example like this also. Okay, so this is common emitter with emitter resistor bypass. This one there is a resistor at the bypass with resistor bypass capacitor. Sorry, bypass capacitor. Okay, so in these cases, we are using the H model to solve. Yeah, in these cases we're gonna use H model to solve. But inside your test, okay, you can use pi model, hybrid pi model. Okay, hybrid pi model, which is basically the same. Okay, basically the same. So what you need to do is only change at this part. Okay, change for hybrid pi model. We're gonna change at this part. It will be okay. It will be v pi r pi. Okay, and at this part we're gonna be gm v pi. All right. And then RB1, RB2 same, and then RC also same. Okay, and then from here you can calculate the input impedance, okay, and output impedance using what we have learned from the uh, hybrid pi model. This hybrid pi model, okay, hybrid pi model, which is so this equation, yeah, R pi, GM, and RO. Okay, so another thing that you need to know is remember about the equation, these equations, yeah. Okay, this equation. Okay, I'm not sure either this equation is given to you during your test or not. Okay, because during your test, usually they will be given. I show to you, yeah, example. Wait, I show to you example. The what? The formula that will give to you. I think in previous tests also there is a formula that's given to you, if I'm not mistaken. There is or there's not? Sharing materials, yeah, show to you for final exam. Okay, wait, I show to you this one. Tab. This one. Okay. Okay, so these are the example. Okay, these are the example of final exam during 2021. No. Yeah. Okay. Why it is 2021? Not yet. No. I think this is the from the previous year, 2020. So these are the example. Okay, these are the example of the questions. Yeah, which I'm gonna give to you later on. Yeah, so you can see. Okay, you can see here in what these questions, how many marks that it's gonna be. Yeah, 5, 4, 4, 3, 2, 3, 4. Okay, so there's lots of mark in these questions, and this is MOSFET, and the list of equation that given to you is this. So it is included. So GM is included, and then AV also included. AVS also included, and also others also. But others is not included. Yeah, others which is R pi, RO, and beta is not included. So please memorize this. Yeah, GM is included. Wait, yeah. Stop this sharing. So GM is included in your equation list. So the one that you need to remember is R pi, RO, and this here, beta equals to HFE. All right. So later on, I will give example on the just now the question just now, and together with the solution for you to try to solve the questions. Okay. For this type of question, you need to try to solve the questions because when you just listening to the explanation, might you don't understand. You might not understand how to solve the equation. So you need to try. So later on, I will give the example of the equations and also the solutions, and try to do the questions by yourself. Is that okay? The one yang just joined just now, I think you haven't recorded your attendance yet, I think. Oh yeah. Any of you haven't recorded your test, your QR, attendance? Okay, can you try to use this link to record your attendance? All right. So any questions? Any questions for today? Oh, yeah, I forgot to mention. I'll since that most of you have chosen based on the survey to do the test not on the same day as the class. Sorry, quiz. Yeah, not test, quiz. So I'm decided to do the quiz on this Sunday. Is that okay? This Sunday, or which do you prefer? This Sunday or this Thursday? This okay, just Sunday okay, all right, so this Sunday. So the test, sorry, not test, the quiz is one whole day. Okay, so I will start the quiz from 9 a.m. until 9 p.m. So from that range of time, from 9 a.m. to 9 p.m., choose 15 minutes. Okay, decide around 15 or 10 minutes to answer the quiz. Okay, but no later than 9 lah, or maybe I can I put until 10 lah, maybe ada yang nak salat tarawih and after that so I'm gonna put until 10. So choose any, it will consider only 30 minutes or 15 minutes like that for you to answer the quiz. So the quiz will cover on chapter 3, which is rectifier, and chapter 4, which is BJT. And the question is multiple choice questions, same as before. So try to attend the quiz, because some of you, I've seen not answering the question, the quiz one. So this will affect your marks, okay? Because quiz, there is marks for your quiz as well. So try to take part, try to answer and submit the quiz too, okay? Because this will affect your marks, overall marks as well. And your test, you have finished calculate the test, and I think most of you have not enough time to answer the questions of question 2, the Zener diode, the Zener diode, and some of you also didn't draw about the the question 3 for the width of the form, many of you, yeah. So please catch up for your another test later on, yeah, your test 2. So test 2 will be after your semester break. Okay, so after this, I think next week, yeah, your semester break. So we will for your after your semester break, there's gonna be another test, which haven't decided the date yet, but around after your semester break, your test. Okay. All right. So any questions related to today? I think for today, maybe you might feel dizzy, or you might feel confused with the formula all this given. But I think you need to try to solve some of the questions by yourself. Look, and if you don't understand, you can just message me through WhatsApp group ke apa ke. So if many of you can't understand, maybe I'm gonna explain in separate video for that, right? Okay, but I want you to try to solve the circuit first, one of the circuit based on the formula given today. so that you can evaluate yourself, either you understand or you don't understand. Is that okay? Okay, so if there's no questions, okay, we will end the lecture today. Okay, and thank you. Ada lagi tak yang tak scan QR code? If there is, kalau tak scan, I will give you. Alright, so thank you so much. Assalamualaikum. Thank you, selamat hari raya. Not finish puasa yet. Thank you.
Thank you, Sensei.
Thank you.